Okay, so what this is that, like, sometimes, right, we can try to solve the problem using two different methods. So for example, like we have method 1, which can, let's say, solve in n square time. Then we have method 2, which can solve in uh uh never mind, I don't know how to use this example. But basically the idea is that, like, you have two methods where one can handle the small case uh very well, and then the other one can handle the big case very well. Then we can merge both methods together to obtain like a decent solution, which most of the time is something like the small case can do small equals to n very well, then the big case can do the more than equals to n very well. Yeah, then uh, let's take a look at the examples. So the first is propagation. Okay, so propagation is like you have a graph, and then each vertex has a number. Then you also have sort of like updates where you are given a vertex and you want to update all its neighbors to have the same number as the vertex. So like this what is let x be an integer return on the vertex. Then after that, for each adjacent thing, replace their integer with x. So it's sort of like you're spreading your number to your neighbors. Okay, so how you solve this problem is you do so for this kind of problem, what you want to do is that you want to speed up the vertices. Let's say you have a vertex with like smaller than square root n. Oh, it's so laggy. Okay, so if you have a vertex with smaller than equals to square root n degrees, right? This is very easy to solve because we can just iterate through all the neighbors. Like we can just do manual update. Like we can just set all of them to x by yourself. So like if like we assume that like the graph is very nice, all of them smaller than equals to square root n, right? Then we can solve this problem is q square root n, because each vertex has a degree of smaller than equals to square root n, and then each update you need to visit all the adjacent stuff which is smaller than equals to square root n. So since there are q updates and each update requires a time of square root n, so this is q square root n. But obviously like the problem won't be so nice. So now we need to consider what can we do about the vertices with more than square root n degree. Okay, so for this case, right, you observe that if the degree is very big, the number of vertices with a very big degree is very rare. So let's say that we have m edges, right, we can have at most square root n vertices which have the big degree. So the number of bad vertices with more than square root n, right, must be smaller than m over square root n, which is roughly around square root n also, because m is roughly equals to n. Like in the worst case, since both of them is smaller equals to 2 times 10 power 5, like based on the constraints. Like this is obviously not true for dense graph, but then like for our analysis, we just consider the worst case, which is smaller than equals to 2 times 10 power 5. So since like the number of bad vertices are very rare, like what we want to think about is there a way to handle these big vertices easily? So the idea behind this is that for the bad vertices, right, since we cannot just do the brute force update because we need to visit all the adjacent stuff. So what we can do instead is that we can store that we uh we can we can store that like update was done to the big vertex, like to the bad vertex. So for each bad vertex, right, we store what is the most recent update plus the number. Okay, so if we can store the most recent update and the number of each big vertex, right, since we only have around square root n big vertex, right, what we can do is that during each update, right, we find all the big vertices. Like let's say we have a vertex, we want to check all the bad vertices. So these are bad vertices. And then since the bad vertices, right, we don't send the update. So what we can do instead is that for each big vertex, we check whether there was an update done on it. So it's sort of like a segment tree where you keep a lazy tag. So like it's sort of the same idea, because like when you have a big vertex, you don't update first. It's only when you have a future update, like when you need to update this, right, you need to know what the actual number is. So we need to visit all the big vertices to check their lazy tag. Their lazy tag is like the most recent update and the number. And we among all the bad vertices, we see what is the most recent update, and we see whether the most recent update is more recent than like what is updated here. So if it's even more recent, then that means that we should do the update. Yeah, so since there are only like around square n of the bad vertices, this means that during each update, like to retrieve the value, right, we only need square root n time. So this is like OQ square n. Are there any questions? Can show the code. Yeah, so you can see for each update, right, we need to retrieve what the actual value for the vertex is. So for the vertex, right, max2 is you take the max of the done and the TI, and if the update is completed then returns true. Like this is a macro that I use, which is quite useful. You can try also. Yeah, so the done X means what's the most recent update that was done to X, and then the TIV is the most recent update done to V. Yeah, then if it's more recent, right, then we need to update the answer. And then the propo is like the lazy tag. Like it's like what we want to for the big vertices what we want to propagate. And then the IMPT it stands for important, which is all the size that is more than equal to square root. So it's like the adjacency list, but we only keep track of the outgoing edges that connects to the big degree stuff. Yeah, then after that, for the update, we only if the size of the adjacency list is more than equals to square root, then we only consider the big ones. But actually, I don't think that's even needed. Try. So we can. So if it's more than equals to log, we can just don't do anything. Compile error. What is this? Okay, never mind. Okay, that is wrong. Why is it wrong? Okay, I'm not sure why it's wrong. I will go and check after the lecture maybe and update you all in the chat. Yeah, but the idea is like around there lah. Like we only update for the degree that's smaller than that. Yeah, are there any other questions? Wait, I submitted to the wrong problem. Okay, yeah, it's correct. Yeah, so if the degree is more than square root, then we don't have to do the update. Otherwise, if it's more than square root, then we just manually update each vertex. Okay, since there are no questions, we can move on to the next one, enumerate triangles. Basically, for all three vertices which are connected by edges between every pair of them, we want to find the sum of AB and XA times XB times XC. So the idea behind this problem is that actually the number of triangles are only n squared n, and we can prove that using small versus big. So our claim is that this only happens in O squared On squared n. So the reason behind this is, first we consider if the degree is very small. Let's say like for each, we consider the case where the triangle is formed by vertices where all three vertices have smaller than actually it's not square root n, it's square root m. Is it? So if the vertices have small degree, right, what we can do is that for each of the vertex, we visit each of the neighbor, and then for each of the neighbor, and then for each of these, right, we mark them as visited. So like and then you need to include this, right? So this is part of the circle. So and then after that, for each of the adjacent stuff, right, you also visit all of its neighbors. And then if the neighbor is part of the visited set, right, that means you already found a triangle. So we will once we already found the triangle, we can go and do the update. So if we only consider like the vertices, the triangles with this property, right, we can analyze that the time complexity is like uh since for each edge, right, we need to visit square root m, right? So this is m square root m, because like even like we don't think of it in terms of the vertices, we think of it in terms of the edge. So for this edge, right, we will visit square root m stuff. And then after that, if we look at this one for this edge, we also look at m square root m stuff. So this is m square root m. So if this is not true, well, actually this the last vertex can be anything. So if our m square m solution can handle the case where at least two of them are smaller than equal to square root m. So if this is not true, right, That means there are two vertex, at least two vertex which is more than square root m. And then if we have two vertex with degree more than square root m, right? Like the number of these, we will call them the same as last time, which is bad vertices. So the number of bad vertices is at most m over square root m, which is square root m. So since there are only square root m bad vertices, right? This means that we can do like sort of brute force. So if each is more than square root m, okay, I think if at least 2 is smaller than if there are at least 2 that is smaller than square root n, right? This means that there are m pairs of bad vertices because you take square root m times square root m. Okay, then for the remaining vertex, if uh,
I don't think that you're sharing the board.
oh wow, the whole time this is okay. Let me go back to the previous part. So this our claim. Actually, I think this should be m squared m or something. Or some around there. Then if we consider the vertices with smaller than or equals to square root m, we can just visit all the square root m neighbors and mark them as visited. Then for each of the neighbor, we also visit their neighbor. So this is so we also visit square root m neighbors, and then for each of the neighbor, if oh wait, okay, now I got it. This also don't have to be square root m. As long as uh as long as only one of them is more than equals square root m, right? Then we okay, wait, let me get back to what I was saying just now. So for each vertex, we mark all the neighbor as visited. Then for each of the neighbor, we visit. If the neighbor is more than equal to square root m, right? Then we visit all the neighbors and we check whether it was visited already. If it was visited already, it means that it's connected to like the same vertex. So this means that we already found a triangle. And when I say it's visited, right, it means that it's directly adjacent to like the vertex we are considering. If we are considering the new vertex, we need to remove the previous visited one and then like get the new visitor set. Okay, and then the time complexity of this is m squared m because for each edge, right, we only consider the vertex if it has smaller than or equals to square root m. So this means that for each edge we only need square root m times. So if this is not true, right, this means that all three vertices are bad vertices. So all three are bad. So we can actually just take m cube pairs, n cube tuples, which is n square m. Yeah. So this proves that the number of triangles is actually m square m. Does anyone have any question? If not, maybe we can move to the next question, which is skyscraper. Okay, so for this problem, yeah, so you want the 0, 1 to reach the Doge 1, and then after that, like the movement that you can do is like based on the power p. So if you have power p, you can move after p steps in front or p steps behind. Then after that, when as like the Doge travel, it can pass the message to other people too, so that you can jump a different distance. Okay, so a naive approach we have is that we can just like do a Dijkstra. So if we start at Doge 0, it has a certain power p. What we can do is that this one is p, this is 2p, this is 3p. Like this one means that you can connect this with h rate of 1, h rate of 2, h rate of 3, because this means that you need 1 jump, 2 jump, and 3 jumps respectively. Yeah, then we can do the same thing for the other Doge. So like, you know, let's say, yeah, then if we like do this kind of
Sorry,
connection,
but you haven't opened the drawing app.
I did it again. Yeah, so as I was saying, right, you can construct a graph so that each you can represent each jump with an edge. So like if the Doge 0 has a power p, this means that it requires 1 jump to reach p, 2 jumps to reach 2p, and 3 jumps to reach 3p. Yeah, then if we construct like the entire graph, right, we can just do Dijkstra on this graph, then we can solve it in like n square. But this is too slow, so we need to use small versus big. So this method, right? This method will work if P is more than or equal to square root n. The reason why this works is that if P more than or equals to square root n, right, then like we'll do until like at most square root n times P. So this means that you only have square root n edges. So now the issue is how do we handle smaller powers? Smaller power. So in order to handle smaller power, we can actually create like duplicate vertices. So these all correspond to 0. These all correspond to 1. These all correspond to 2. Then the reason why we want to create duplicates is that we can use it to indicate like the current power we are at. So for example, right, like this layer, this means that we currently don't have any power. So the only edges that we can use are those that are more than equal to square n. So now if you want to use something that is smaller than equals to square n, right, we need to go to its appropriate layer. So let's say we want to use something that is of power 2. Let's say those 0 has power 2. If you want those 0 to be at power 2, then we need to go to this layer, power 2 layer. So the power 2 layer, right, it will connect 2 steps away. And it will continue connecting to power 2 because at this vertex, right, it also can go to, like, it can continue jumping. So, like, this means that at I means power I. So, so if you have node x at layer I, you need to connect to x minus I and x plus I, both at the same layer. So if you do this, right, this means that each vertex at like this layer, right, only has like around only has one edges. Then it's only at like the bottom layer, which is layer 0, where you have at most o square and edges. So at the same time, the number of vertices is also n square n because of the number of layers that you create. So the number of edges and the number of vertices are both like n square n. So if you do the extra with this, then it's like n square n times log, which should be enough to solve this problem. Any questions? Now we can move on to Bitaro's party. So this is uh quite a hard problem, I think. It's not loading. So this problem is like you are given a directed acyclic graph and you sort of want to calculate the longest path from any any vertex to a certain a certain vertex. So it's like the jth party is held at tau tj, uh, and then you want to find like the longest path lah. But the hard part of this problem is that there is a set, so it like yj friends are too busy. So what this means is that like basically you want to find the longest path to a certain vertex. But at the same time, there are some set of vertices where you cannot start from. Yeah, so like in the input is like 411 means that you want to find the longest path from any vertex to vertex 4 except for vertex 1. So you want to find the longest path starting from any vertex other than vertex 1 that ends at vertex 4. So in this case, it means that you want to find the longest path starting from any vertex except for vertices 2 and 3 that ends at vertex 5. First, let's consider how we will solve this problem if we don't have the constraint of like which vertex that we cannot start from. So we assume that we can start from anywhere. So the way that we solve this is that we can do a DP. So our DP stores the longest path that ends at the vertex. So at the start, right, this means that the longest path is like 1 itself. And let's say this one, it has a vertex here. So you can update the DP to be 2. And let's say this one also has a vertex here. So this one you also update to be 2. Then let's say you have this one which is like that. Then this one you need to see for each of the edge, right, which one is larger. So since 2 is the larger one, this means that the longest path that ends at this is 3. So you do the same thing for like each of the vertex, then you can get the answer. So the problem now is that uh, there are some vertices which are blocked. So maybe like even though this is 3, right, what if actually this is one of the vertices that cannot be used? How can we handle that? So we need to use small versus big. So let's assume that what is it? We assume that the size of the set uh is I think in the problem is t or y. This y is the number of illegal start vertices. So if y is smaller than equals to square root n, right, we can actually come up with a similar algorithm as we came up above. But instead, like because what we are storing here is like the longest path. What if instead of the longest path, we store the uh, top square root and longest path? So in this case, instead of storing 3, we can store 3 and 2 because and then actually also like 1. Actually there are two 2's. Actually, I think off by 1. Okay, this should be 0, 1, 2. No, this also 1, 2. Yeah, so instead of just storing 0, 1, 1, 2, right? So for the source is the same, we can only store 0. But for this one, right, we can start from itself also. So the longest is like 1 and 0 because you can start from here and then the longest part will be 1, or we can also start from here and the longest part will be 0. Then for this one is the same, 1, 0. Then for this one, right, like the longest path is like if we merge from here, it will be 2 and 1. Then if we merge from here, it will be 1. So this means that if we start from 0, we can get a path of length 1. If we start from 1, we can get a path of length 1. But if we start from 0 and then go to 1 and then go to 2, then we can get a path of length 2. So like instead of like what we did previously, which is just take the max, right? What we need to do instead is that we need to like store a vector instead. We store a vector of size square n, and then whenever like we come to a new vertex and then we want to update, right? What we need to do is that we combine all the entire list, right? Like from multiple vertices, we combine their lists into a single big list and then reduce the size to square n again. So if we do this, right, then if the number of illegal starting vertices is smaller than square n, right, this means that we can always find which one is the answer because we can just loop through the entire list. Like if the list is square n, right, we can just loop through the entire list. Since y is smaller than square n, at one point one of the vertex will not be part of the illegal set. So yeah, so if you pre-compute this information, we will be able, like during each query, we can just loop through the entire set, which is only square n times. So it's like the pre-computation requires square n, and at the same time each query also requires square n. And then after that, for the y that is more than square n, right, actually this is even easier because the number of stuff that this can happen, right, is smaller than 2e5 over square n because there's the constraint that the is it 2e5? No, it's 1e5. There's a constraint that the sum of y, right, the sum of y is smaller than equals to 1e5. So the cases where this happen is 1e5 over square n. So what we can do is that we can do the naive dp that we did earlier. We can do this dp, but we manually delete the illegal vertices. So for each of those cases, we just do the dp again on a different graph because like some of the vertices are missing. Yeah, so that's it. Are there any questions? Can see my code here. So for the first part, we are doing the pre-computation of the square root n longest path. So like the part that I'm doing here is sort of like merge sort, like the merging part of merge sort, because we have two lists, we have two sorted lists, and then we want to merge them into like one big sorted list. So this is like the same code as like the merge in merge sort, and after that we only maintain like the smaller than square root. Yeah, and then after that, if y more than equals to square root, then after that we just do like the normal DP. Like if just do the normal DP, then if the if it's like the illegal one, then we just ignore it, otherwise take the maximum. And this one is using the pre-computer one. Okay, since there are no question, I'll move on to the rebuild. So what rebuild means is that